Hi, this is Mr. Yeoman, and on a rainy Sunday afternoon, I am here to talk to you about how to predict products of reactions. Previously, we had discussed the five major types of reactions, which include combustion. So, quick refresher here. That includes combustion, synthesis, single replacement, double replacement, and decomposition. Okay, so each one of these have certain characteristics that they typically follow through. So I just want to talk about a couple of those. Combustion, most people know the word combustion. So it really just means to burn. That could be burning something slowly, or it could be like an explosion where it burns very quickly. But chemically, they do the same thing. So no matter what, we're going to have some sort of hydrocarbon. Okay, and so a hydrocarbon by definition, is a hydrogen and carbon. Okay, uh, sorry about that. I miswrote there a little bit. So a hydrocarbon, and so it could be the simplest hydrocarbon, which might be methane. Okay, CH4. That's one of the simplest ones. Um, or it might be something bigger. It really doesn't matter what that is. One of the examples that I use sometimes in biology is looking at sugars, that we intake sugars and we are essentially burning those. We talk about burning calories, and even though we don't actually light them on fire, we are releasing energy, and this is the same concept. We require oxygen, and through that process, we are going to be breaking down sugar into simpler types of energy. So we're releasing it in a slightly different way, but the big picture is more or less the same. So you take any sort of hydrocarbon, and it really doesn't matter which one, and you're going to be combining that with oxygen. And the result is always the same. We're always going to have the same two products, carbon dioxide and water. So there's some carryover here. If we want to use that reference of biology, we take in oxygen, we produce carbon dioxide, and we also produce water. So this really is reflected more or less in the biological setting as well. But the nice thing about combustion reactions is that this part of it always looks the same. You're always going to be combining with oxygen, and you're going to be producing carbon dioxide and water. That's always the case. The only thing that might be a little bit different is which hydrocarbon you're using. And so it could be any of a number of other hydrocarbons as well. These are just two examples that I chose, two very simple samples. Um, very, very simple type of reaction. Okay, synthesis is a little bit different. It is a simple type of reaction where you just combine a couple of elements. And so the concept of synthesis is really just that you're going to have at least two compounds, two atoms maybe, so that might be elemental, or you might have small compounds. It really doesn't matter. But in the result, you only have one product. Okay? Or some people might look at that and instead of putting C, I could put A, B because I really combine these two together. And it doesn't matter the order. I could have had this written as B plus A forms AB. So don't get caught up on the order of the letters, but I'm trying to get you to think about the concept of I'm putting this information together to make a single product. Okay, I probably should have put decomposition next, because it's really just the opposite of synthesis. We don't see it quite as often. It's harder to measure. We just don't use it very often in chemistry. Uh, at this low level of chemistry, we're looking more at the single and double replacements much more because we can see those a lot easier. But it's really just the opposite, is that you're starting with a single reactant and you're going to break it apart into multiple pieces. Um, Single and double replacement reactions are really self-explanatory. So I'm going to still end up with a compound, and I'm going to have something that's by itself, so some sort of elemental reactant that is in here. Now, this elemental reactant is going to replace, hence the name replacement, is going to replace one of these two. And which one it replaces is going to depend on the charge of C. So if C has a positive ionic charge, then it is going to replace whichever one of these two is also positively charged, which the way it's written right now would be the first one, because in a compound, the first element or the first ion is always the positively charged ion, and the second ion is always the negatively charged ion. So if C were positive, it would replace A, because you can't have two positives together, so that would make no sense for C to replace B, because A and C cannot combine together, because they would repel due to their similar charges. If C had a negative charge, it would end up replacing B. Okay, and that's what we're going to assume for right now, is I'm going to say that C has a negative charge, A has a positive charge, B has a negative charge, so these two are really going to be switching places. And so what that results in is now I have A and C together, and B is going to be by itself. Okay. Double replacement is really no harder. The only difference is that in this case, C is combined with something else. Okay, and so I'm just going to arbitrarily make this positive, negative, positive, and negative. And just like before, we can't have a positive replace a negative, because that would end up having two positives together and two negatives together. It's a double replacement reaction because two of them are going to be switching spots, but the other two are switching spots as well. They're not really switching spots, because if these two switch spots, then what would happen is you just want to recombine who is with whom. Okay, so in this situation, we would end up with C being our positive that is going to be with B, and A is our positive that is going to end up with D. Okay, so this is where it's going to be important for you to know which ones have positive charges and which ones have negative charges, because if you don't know that, you're going to have a really hard time predicting what your products are going to be. Okay, so that was kind of a brief introduction to that, but let's try a couple samples here. We want to try one of each type. So this is in that booklet that I gave you earlier in the semester. The sheet is in there, so if you want to follow along, you're welcome to do that. I'm not going to do all of them, but this would be a great opportunity to get in some practice and have me check that out before we move on and take our next quiz. So the first one I have on here is a single replacement reaction. Now, if we refer back to this, we know that a single replacement reaction has two things that are combined, something that is by itself, and that element that's by itself is going to replace a like item in that compound. Okay, so in this case, C being negative replaced B, which was also negative, making A and C together and B by itself. So if we take a look at this one, you don't actually have to write this in, but I'm just doing it just to kind of think through. Silicon has a positive charge, and iodine has a negative charge. Okay, we know that because the positive ion always goes first, and so we have iodine being our negative charge right next to it. Next, we have magnesium by itself. So we need to determine what magnesium's charge is. So if we take a look at our handy-dandy periodic table here, we have magnesium right here in our second column. So we have everything in the first column having a +1 charge, everything in the second column having a +2 charge. If we skip over to some of these other columns, then we can continue that trend. So we have +3, ±4, -3, -2, -1, and the noble gases, as always, have no charge, so they don't react. But the one that we care about right now is magnesium having a +2 charge. So if we come back to our problem here, magnesium has a +2 charge, so it is going to replace one of these two. Magnesium being positive means that it is going to replace silicon. So I'm going to end up with magnesium and iodine together. Okay? A really common mistake that occurs right here is many people want to write MgI4 because they see that there's 4 iodines over here, so obviously there has to be 4 iodines over here, but that's not the way that it works. If you think back to when we were trying to form ionic compounds, then I had that set of cards that had charges on them. So if each line here on my paper counts as a charge, then I could have magnesium right here. It has a +2 charge. Okay, well, iodine, being a halogen, okay, all the way over here in our second to last column, has a -1 charge. So it is only going to take up one of these lines. Now, if I tried to put 4 of them here, there would be way more iodines than what I would need. So I'm only going to put 2, and that is going to balance out our charges between magnesium and iodine. So in my formula, I'm going to put a subscript of 2 right behind iodine, showing that magnesium and iodine are in a 1:2 ratio. Now, being a single replacement reaction, silicon is going to be by itself, so it'll just be hanging out over here. But we still have to balance our equation because since we didn't put a 4 here because that wouldn't belong there, then we need to put coefficients so that we can have this all balanced out. So looking over here, we have 1 silicon on the reactant side, 1 silicon on the product side. We have 4 iodines on the reactant side, and we only have 2 iodines on the product side. So looking at that, I need to make this 2 into 4. So what I'm going to do is put my coefficient of 2 in the front here, and it doubles this entire compound. Okay, that's why we went through and we were talking about balancing, because this is where we're going to be using that, is that we need to make sure that we double that entire compound. So now we have 4 iodines on this side, and we have 4 iodines on this side. That brings us to magnesium. We have 1 magnesium atom and we have 2 magnesium atoms. So we come back over to this side and put our 2 as a coefficient, and we are now balanced. We have correctly predicted our product and can identify what those products are going to be and balance that equation. Okay, I'm going to jump down here to number 3. Because it kind of uses the same type of problem-solving strategy that 1 used. We have copper 2 chloride and potassium hydroxide. Okay, and it being a double replacement reaction, we can look back over to our notes here. We know that we're going to have a positive and a negative, so this would be our copper 2 and our chloride, and then this would be our potassium, and then our negative is the hydroxide polyatomic ion. So they're going to switch places. And it doesn't matter which one comes first. We just want to make sure that when we rewrite it, that our copper is going to be with our hydroxide and our potassium is going to be with our chlorine. So I'll just go ahead and write copper first, but as I said, if you wanted to write potassium first, that would be absolutely fine as well. So copper has a +2 charge. But Mike, you say, how do I know that copper has a +2 charge? Well, looking at our formula here, I have 1 copper and I have 2 chlorines. So if we use that same box method that we were looking at before, we had CuCl2. And so chlorine, we know, again, based on the periodic table, has a -1 charge. So it is only going to take up 1 square. But there are 2 of them, so it's going to be 2 squares, 1 square for each chloride ion. Okay? There's only 1 copper. Now we know in order for this compound to actually form, we need our negatives and positives to be balanced out. So our copper is going to take up the same amount of space as our chlorine. So looking at this, we know that our chlorine and our copper are balanced, so that means that copper has to have a +2 charge. Okay, so looking at this, copper has a +2 charge, and so I can take a look at hydroxide. So if I take my periodic table here and I flip to the next page, On the back of that, I have common polyatomic ions. Okay, right up there at the tops, I have positive ions on one side, I have not negative ions on the other, and since I'm looking for hydroxide, I am going to come over here to our negative side. There is OH minus, meaning that hydroxide has a -1 charge. Well, if hydroxide has a -1 charge, that means I need 2 of them here in order to balance out with my copper. Okay, so that my charges are the same. Okay, so that takes care of my copper and my hydroxide. Now, potassium and chlorine are going together, and again, very common mistake, people want to put that 2 behind there because they see a 2 over here, but that's not going to work. Okay, potassium has a +1 charge, chlorine has a -1 charge. So I'm sorry, I'll say that again. Potassium is a +1 charge, and chlorine has a -1 charge. So those charges are going to even out. So we don't need more than 1 chlorine here. If we did, that would be incorrect. We want those charges to be the same. So now we can go back and we can balance. Well, looking at this, I have 1 copper on the reactant side, 1 copper on the product side, because this 2 only applies to my hydroxide. That's why I put the parentheses in. My chlorine, I have 2 of them. I only have 1 over here, so I'm going to put a 2 in front. Okay? I only have 1 potassium on this side, and now I have 2 potassiums over here. So I'm going to put a 2 here. And now I have 2 oxygens and 2 hydrogens. Well, on my product side, I have 2 oxygens and 2 hydrogens. So that's going to even out as well. Okay, so there is a single replacement reaction and a double replacement reaction. All right, moving down to number 4 here, decomposition. So we're going to break this apart. And just like we talked about before, you start with a single compound, and it is going to break apart into its components. Now, sometimes those components are elements. Sometimes they are larger pieces like carbon dioxide. But in this case, it's a very simple one. We only have 2 elements in our compound, so we don't have a whole lot of choices. This ammonia, NH3, is going to break apart into nitrogen and hydrogen. Now, this is a little bit tricky because unless you remember our covalent bonding rules, you may not remember that these are both diatomic atoms. They're diatomic elements. So when they're by themselves, there's always going to be 2 of them. And a simple way to remember that is that if it ends in an En or an Ne, it's diatomic. And the reason for that is, I'll come over here and write that, nitrogen has 5 valence electrons. So it is currently not stable. But if there are other nitrogens hanging around, which is usually what happens, you don't typically have a single atom just running around. There's usually several of them. They can share these electrons, and now they're both stable, making this N2. Hydrogen works the same way, that we have a single electron. Hydrogen's a little bit different. It doesn't follow the octet rule because of the energy level that it's in. It only needs 2 valence electrons. But same idea, there's another hydrogen floating around with it. If they share electrons here, they are now stable, and so we end up with H2. Okay, like I said, that's the reasoning for why they are diatomic. But a simple way to remember that is if it ends in an En or an Ne, they're typically diatomic. So just keep that in mind. Now we can go back and balance our equation. So we have 1 nitrogen and 2 nitrogen. So I'm going to put a 2 in front here. So my nitrogens are even. Now I have 6 hydrogens and only 2 hydrogens on my product side. So I put a 3. We're balanced. Easy as eating pancakes. So we've now covered 3 of our 4, 3 of our 5 reactions. The one that I want to do, I skipped over this synthesis reaction because antimony acts a little bit funny. It can take either a +3 or a +5 charge. So I just wanted to stay away from that one for a second as an introduction. But I'm going to jump down here to synthesis reactions. And as we discussed, synthesis reactions take 2 things that are by themselves and make a single product. So in this case, we're going to put zinc and oxygen together. Now, The typical mistake that is often made is somebody wants to put that together to make ZnO2. So they're like, all right, we're just going to put these together. So that's what happens. I take these two things and I put them together. But that's not the way that it works. Zinc has a +2 charge, which you can find on the back of your periodic table. It's a transition metal, so you can't just look at it on the periodic table and say this is what charge it has. But on the back of the periodic table, down here at the bottom, zinc has a 2+ charge. Okay. Oxygen, however, because of its location, I mean, you could look on the back of the periodic table and see that oxygen has a -2 charge. But if you wanted to, you could also go look at the periodic table itself and see that oxygen, that is right over here, has, well, this column has no charge. Halogens, -1. The oxygen family has a -2 charge. So two different ways that you can find the charge for oxygen, but it's just going to come in handy for this particular problem. So if zinc has a +2 charge and oxygen has a -2 charge, then we only need one of each in order to make our product. So it's just going to be ZnO, that's zinc oxide. But, as you're saying in your head, I hope, that we have too many oxygens on this side and not enough oxygens on this side, so we can just solve that by balancing. So now I have 2 oxygens on my product side. However, now I have 2 zincs on my product side and only 1 zinc on my reactant side, so I need to put a 2 out front there. Okay, so I'm hoping that's making sense. Last one, and I saved the easiest one for last here, is a combustion reaction, because as I said, combustion reactions always have the same product. We glance back at our little cheat sheet here. We have a hydrocarbon. In this case, our hydrocarbon is propane, C3H8. That is our hydrocarbon. And it is combining with oxygen just like it did in our sample. And as always, these combustion reactions are going to have the same result. It's going to be CO2 and H2O. So there's really not a whole lot of figuring out to be done on these types of products. That what becomes difficult at times is balancing this. And so that does become an issue at points. So let's try to figure this one out. So we have 3 carbons on our reactant side. We only have 1 on the product side, so that's going to be a 3 right there. Our hydrogens, we have 8 on one side, and we only have 2 over here, so I can put a 4 over here. So now our hydrogens are balanced. And so we have 6 oxygens plus 4 oxygens is a total of 10. So I can put a 5 out front here, and I now have a balanced chemical equation for a combustion reaction. Okay. Down below here, this is going to help prepare you for your class action lab that we're going to be doing here. Lithium metal reacts with liquid bromine. This is just a word equation. This is typically what you get when you have some sort of chemical demands put on you. Somebody will tell you, this is what I want done, and so you have to interpret that into what type of reaction that's going to be, or what that chemical reaction is going to be. So we're just trying to recombine this. So lithium metal, okay, so we just need to figure out what the symbol for lithium metal is. Okay, so I have lithium, that's Li. So I'm going to put Li, reacts with, it's going to be plus, liquid bromine. All right, so bromine is over here. It does happen to be a liquid at room temperature, and so our symbol is Br. However, bromine ends in an Ne, so that's an easy way to recognize that this is going to be diatomic. Okay, based on what this is, the product should be fairly easy to determine because we have 2 elements by themselves. There's no replacement to be done because they're not already compounds. They can't decompose because they're already in their simplest form. They're not combustion reactions because there's no oxygen present. So we're really left with synthesis. So we're going to put lithium and bromine together. lithium having a +1 charge and bromine having a -1 charge gives us LiBr, lithium bromide. Okay, again, we balance and easily solve that. Okay, I hope this helps you out. If you have questions, please let me know, and we can find some time to work together. Have a great night.